Today we will talk about simple harmonic motion and oscillations. Our learning objective is introducing some common examples of a simple harmonic motion, to define some common terms such as period and frequency, and to think a little bit about the phase relationship between displacement, velocity, force, and acceleration. Well, do you know some simple harmonic motions? There are many examples in daily life. For example, a child on a swing, a Mars on a spring, a simple pendulum, or even a boat rocking side by side on the water, or a ball rolling from side to side in a dish. Depends on the shape of the dish. Okay. Now we have two important positions in oscillation. We have the maximum displacement and we have the equilibrium position. Yeah, think about a child who's doing a swing. When he comes at the highest point, that is the maximum. When he's at his lowest point, he's at the equilibrium position. Yeah. Okay. So we can say that the child on the swing is to say that she is, or it is oscillating about the equilibrium point. Okay. Some definitions. The amplitude, obviously, is the maximum displacement from the equilibrium position. We have the period t, that is the time for one complete oscillation, and the number of oscillations per second. Another oscillation, the bungee jump. Okay. So how would we describe the motion of a bungee jump after he leaves the platform? How can you initially describe it for an ideal world? Or how could you describe what is observed in real world, account for the difference between ideal and real world scenarios? Obviously, ideal would be if we have a perfect oscillation and the amplitude is always the same. That means there's no friction. That would be the ideal situation. Obviously, in most cases we don't have an ideal situation, but we'll talk about that later. I'm not going to look at this one, but you can look at the FET Colorado, and you can look at the oscillation of a mass that is hanging around on a spring and is moving up and down. What do we mean by phase difference? Now imagine two twins swinging on identical swings. Since the swings are identical, the oscillation motion will be the same. However, when they oscillate out of phase, the twin reaches the maximum displacement at delta t seconds behind the other. So we can actually a phase difference, we can express it in 2 pi delta t over the time period, and that is the phase difference. Small question. We have a mass on a spring. It is displaced, takes 9.6 seconds to complete 20 swings or oscillations. What would be the time periods? The frequency of the oscillation. And let's say we have two identical pendulums in which two complete cycles have in 16 seconds. What would be the phase difference if AX passes through equilibrium 0.2 seconds later than y, or x and y both reach maximum displacement at the same time but in opposite position. Think about it, how you could calculate that. It should not be too difficult. You know what is the time period? That is 9.6 divided by 20, you get the time period, and then you can make use of the 1 over time period and you get the frequency. Okay. And for the phase difference, you can use the formula that we used before. Yeah. So that is 2 pi delta t over the time periods. Okay. Thinking about SHM, simple harmonic motion. What is it that causes a displaced object to return towards the equilibrium? We have the gravity. When is the velocity of the object at maximum? That is, of course, at the equilibrium point. When is the velocity of the object at minimum? At the far ends of the oscillation. Is the velocity constant or does it change based upon other factors? The velocity is constantly changing from 0 to max and then from max to 0. Okay. Thinking about SHM again. What do you think? What would be the displacement? What would be the velocity? What would be the force? And what would be the electric acceleration? If we have at the maximum left, that means displacement is max. When we are at the maximum left, the velocity is 0. When we have at the maximum left, what would be the force, and what would be the acceleration? Next and max. Oops. Next. What will happen in the center or the equilibrium point? Displacement is 0. Velocity is maximum. The force is 0. Oops. Don't want to see this. Is 0. And at equilibrium point it is 0. And of course for the maximum right we have the same as the maximum left, only in opposite direction. Okay. Simple harmonics. How to arrive to a relationship between the displacement, velocity and acceleration for a system in SHM. How we'll be able to calculate the magnitude direction of the acceleration at any time of an object in SHM. I'm not going too deep into these formulas. These formulas are mainly discussed in IB, but just let's have a look at the applets. Oh, still playing. Sorry about that. When we look at the displacement graph and the amplitude, we see a nice sine or cosine curve. Okay. We see the displacement. For example, at t is over 2, we get maximum displacement, and at t we get also maximum displacement. This is a way of showing a simple harmonic motion. Yeah. So how do you think the velocity and acceleration on the same axis would look like? Here we have the displacement, And then when the displacement is 0, the velocity is maximum. When we are at equilibrium, the velocity is at 0. And we can compare the graphs. We can also compare here another one, and you see the relation between the displacement and the velocity. Okay, as we had all said already, the velocity is the greatest when the gradient of the displacement graph is the greatest, which is at the equilibrium point. Yeah, the velocity is 0 when the gradient of the displacement time graph is 0. Okay. A little bit about the acceleration. And again, when we have maximum velocity, no force is working, that means that the acceleration is 0. When we have a velocity of 0, then we will see actually that the acceleration is maximum. And here again we can compare the three graphs with each other. Okay. It's just to show how is the displacement related to the velocity and to the acceleration. Okay. Okay. Remember that the acceleration is the greatest when the gradient of the velocity time is the greatest. Yeah. And the acceleration is 0 and the gradient of the velocity time is 0. Okay. Okay. One thing we know for simple harmonic motion is that the acceleration is always in the opposite direction to the displacement. So, in order to define an oscillating motion which is SHM, harmonic motion, we know that the acceleration proportional to the displacement, always in the opposite direction to the displacement, and we see the correlation. Yeah, and so we can relate the acceleration minus a constant times the displacement, which we will come to that in a moment. And here we have our formula in order to calculate the acceleration, and you will see when you put a graph of the acceleration with the displacement, which is x, we can simply rewrite the formula. Remember that the acceleration is v squared over r. V is related to r times w, rotational motion. So a is w squared divided by r. W is 2 pi f. So acceleration is minus w square x. If we would put a graph of the acceleration versus the displacement, let's make my graph here. There's the graph. We get a line through the origin. Has to go through the origin, just mentioned that. Here we have minus x0 plus, and then the gradient is minus w squared. Okay. Okay, so the acceleration is minus angular velocity squared times the displacement. So, the following question. A mass on a spring oscillates in SHM with an amplitude of 35 millimeters, the period of 2 seconds. If it passes the equilibrium in the upward direction at time is t0, what is the displacement of the object? 1/4 of a cycle later, 1/2 cycle later, 3/4 of a cycle later, and 1 cycle later. Calculate the frequency. B. The acceleration when displacement is plus 25 millimeters and minus 25 millimeters. Well, we use a formula. We know the time period, so the frequency should be 0.5 Hertz. Then we can calculate the acceleration at 25 millimeters, that means at maximum, and this is minus 25 times 10 to the negative 3 pi square meters per square seconds. And the same to the other side, so how many have the other should be then 25 times 10 to the negative 3 pi square meters per second. You see that we have chosen the direction for the acceleration, so for the plus we say it's negative, and in the opposite direction it is negative, so the acceleration is in the opposite direction. Okay. For the next question. Simple pendulum oscillates in SHM with an amplitude of 32 millimeters. It takes 20 seconds to complete 10 complete oscillations. Calculate the frequency. That is, of course, 0.5 Hertz. What would be the initial acceleration? Well, we use a formula and we will find that frequency, figure that out, is minus 0.316 meters per square second. Then, if the pendulum is released at the time is 0, state the displacement, calculate the acceleration when t is 1 or t is 1.5. We're not going to discuss that too much, but you could figure it out. I only want to show you this graph, but we are not discussing this in A level. If we have a simple harmonic motion and we have for the relation of the displacement x, then x is amplitude times sine wt. If we want to find the velocity, then we get velocity is a times w cos wt, and if we find the acceleration, we will find a minus a square w square times sine is wt. Okay,